need to go into the middle.
Hi, probably can guess where I am. I've tried not to do it from home today. We're going to carry on with our stored elastic energy. And I can work, which is really nice. Hopefully we'll all be back soon. So we're going to start off with a few examples of other things that we could have done. So we did Perky, because this is what you asked for last time. Here was this lovely little creature here, because he stores elastic energy within him, and he went up about 70 centimetres. It's random, because the spring stores the energy and then changes it into gravitational potential energy, or kinetic, and it gains gravitational potential energy. This one here is called Perky. Now, Perky has got a mass of 9 grams. I just popped him on the kitchen scales. Remember, when you're doing your calculations, you need to change that to kilograms. He can squash, he's 5 centimetres tall to start with, and when he squashes down, he goes down to 2.3 centimetres. So you have to work out the difference for the extension when he's squashed. Perky only goes up about 50 centimetres, and bear in mind gravity on Earth is about 10 newtons per kilogram. So, when you come to work out the energy changes for Perky, I'll pop him on there, look. He does go up about 50 centimetres, we measured him earlier.
Wow.
First of all, you have to work out, my handy helper over here is not listening, you have to work out the gravitational potential energy gained by Perky. So that's GPE, which is equal to the mass times the gravity times the height. His mass was 9 grams, so we've got to change that to kilograms, that's 0.09. Gravity on Earth is approximately
10.
Is approximately 10 newtons per kilogram, and the height he went up to was 0.5 of a metre, so I'm going to put 0.5 on there, okay? Brilliant, so you put that in your calculator and you get 0.45 of a joule, because it's measured in joules. Now, this is the bit they'll ask about with elastic stored energy. Your 0.45 will then equal the energy stored in the spring, which is a half times k times x squared. Now the x is the extension, and that's how much he's squashed by, the difference in the height at the beginning and the height at the end. K is what we're trying to work out, that's the spring constant for Perky, and then we know the energy stored in it is 0.45 joules. Pause the video and have a go now. Please don't stop recording. The answer is just over here on the board. So I had, my extension was 5.5 minus 2.3, which gives you 2.2 centimetres, which is 0.022 metres, and that is your x. The energy, which was 0.5, is a half times the spring constant k times 0. Missed out the 0.22 squared. I did put it in when I did my calculations. Okay, so there's a 0 in there. So when I put that in my calculator, on this side, I got 2.42 times 10 to the power of minus 4. So then that needs to be divided, 4.45, you have to times it by that side, so you have to divide it by for this side. So I did 0.45 divided by 2.42 times 10 to the minus 4, and I got 1,859.504132. Now, do you think you need all those decimal places?
Wow!
Do I need all those decimal places?
If you could put a recurring sign in,
I'm not doing a recurring
you can't do that in silence.
How accurately did I measure all my things to? How many numbers have they got?
2.
2, brilliant. So, should I round my answer to 2?
Yay!
So ideally it'll be 1,900, and because it's a spring constant and we've
Do you
done it in
know,
metres,
rub it out and write it down.
it would be 1,900 newtons per metre. Brilliant. Right, well done, very good. So, I've got one more here. This one is called Lighty, because he's very light. When I popped him on my kitchen scales, he only had a mass of 3 grams, so I just turned on, made sure it was in grams, popped him on. They're not very reliable, they keep coming up in... Put him on there. Oh, now it says nothing, look. No, 3 grams, perfect. So
3
I've got
grams.
him as 3 grams. So, Lighty has got a mass of 3 grams, so when we're trying to work it out in kilograms, we need 0.03. His normal height is 8 centimetres. I got my ruler and I measured him. And then we squashed him down. He squashes down really, really quite small. He squashes down to about 2.3 centimetres, and then he's amazing. He goes super high. So we had to work out the difference.
I don't want to pick him up.
No, it's fine. Work out the difference there. So the height reached when we did this was 1.2 metres. Gravity on Earth is approximately 10 newtons per kilogram. So now, all you have to do is stop the video and have a go and see if you can work out the spring constant. Work out the gravitational potential energy gained, which is the mass times gravity times height, and then that will be equal to a half kx squared, because that's the elastic energy stored. Okay?
Cool.
Hopefully when you do that, you will get the GPE.
What's a GPE?
The gravitational potential energy gained will equal 0.36 joules. That will then equal a half times kx squared. The x is the difference in height, so it's 8 centimetres minus 2.3 centimetres. So I think that was 0.45, 4.5?
Yeah.
It was 4.5. I think that was 5. So we ended up with 0.045 for our x, but remember you have to put it in squared. And hopefully, K, for this one, you would get as 355.5 reoccurring. Now, can we have a reoccurring number? No, not for GCSE science. So we measured it to 2 significant figures. So should our answer be to 2 significant figures?
Yes.
So K will be approximately equal to 360 newtons per metre. Brilliant. That hopefully goes through the rest of the potential elastic stored energy bit. What we're going to do now is look at the second bit on your core practical. So we need to just have a look at the next thing, which is the stored energy inside a ball. Now, the second bit is about, the aim is very scientific, this, is to find how squashy a tennis ball is. So this is the actual, I will email you the sheet, I'll put it on Google Classroom. To measure how squashy a tennis ball is the actual aim on the sheet.
Wow!
So we're going to have to adapt it slightly as usual. Come on. Oh, my handy hat, go on. So, on the sheet that I've given you, it says you need a rubber ball, tennis ball, large cube, board masses, some masking tape, and you have to set it up a bit like this. However, I did mine a bit differently, because irrespective of how many times you squash a tennis ball, even if I put my massive, and this is really heavy, thing for chopping up the wood at home on my tennis ball, it doesn't squash very much. So you're not going to get very good results. However, I do happen to have these foam tennis balls at home, which I've used quite a lot. I tried lots of different balls. I tried the really bouncy orange one. It's got very high elastic constant, so it won't squash very much.
So it's basically a plastic flicker ball.
Yes. This one is brilliant though.
It's made out of foam.
It's foam, so it squashes quite a lot. So what I did was I taped on a coaster, it's very scientific, inside of some sellotape, I taped the foam ball inside so it doesn't move, so it's stuck on there, so it's perfect. And then what you have to do, and the aim in the method, you just put, I used another coaster because I had these at home, pop them on top, and then you have to measure the 4 corners of your coaster or your piece of wood with no mass on it, and then you have to gradually add masses onto, and then after you've added a mass, I had some very good handy helpers, and we measured the corners all at the same time. So you have to think really carefully. As you add more mass onto the top of your ball, it's going to store some elastic energy because it gets quite squashed. So every time I add more mass, I had to measure each 4 corners and then calculate the mean height. So I did it up to 5, and actually it got quite squashed. So I could put this one on as well.
Okay, now that is squashed.
That is quite squashed. Now when I take them all off, have it's gone past its elastic limit?
Let's find out.
Or will it get back to the same as it was before? Make sure, I have put this, I'll take a photo because I've done this and I've got a table with all the results in it for this because you will need to plot a graph. When I take them all off, they're a kilogram each, and is my ball the same again, you think?
Yeah.
Brilliant, so it hasn't gone past its elastic limit. I have got a results table that looks just like this. We've got mass and weight, corner 1, corner 2, corner 3, corner 4, and the mean, okay?
Mean.
And I've put it on there, so you'll just have to didn't teach my handy help how to do this. Have a look at the results table here. So have a really good look at that. I put a mass of 0.1 kilograms, 0.2, 0.3, 0.4 and 0.5 on, and then we measured each of the corners in centimetres. Oh, I've been really terrible, I haven't put my centimetres on there, have I? So I'll put my centimetres on there. Terribly sorry if you can't read any of the numbers, it's not my fault today. It's my handy helper who's doing a brilliant job. So you'll need to work out the mean height down here. You'll need to also add 0.1 of a kilogram, the weight in newtons. Remember, you times it by 10 to get mass to weight. So that would be 1, that would be 2, that would be 3, that's 4 and 5. I'll take a photo of this and put it on in the PowerPoint for Google Classrooms. You'll need to calculate the mean height. Ooh. And then you will need to plot yourself a graph, of course, as always. So on your graph, you need to have force on your x-axis. So that will go from 0, 1, 2, 3, 4 and 5. And up the side here, you need to have the mean height. So the mean height I think we started with was about...
8. Just
perfect.
Can be 8.
Could be 8, and we could go up in 2s or whatever it is, go up to 8 on the side. Now you have to think really carefully about what shape your graph is going to be. Is the mean height or the difference in height going to be directly proportional to the force added or not? Bearing in mind the mean height is to do with the extension. Now I hope that you'll remember the shape of the graph will be something to do with the half kx squared. So the extension is squared. So think about your maths. What's going to happen to the shape of the graph? I will start with the shape of the graph at the beginning of the next lesson. So ideally, you work through the PowerPoint, have a go at the calculations at the beginning. You will also then copy the results table down into your exercise book, calculate the mean height and plot yourself a graph. Hopefully I'll be able to see you very soon. Thank you ever so much to my handy helps for today. Oh, before I go, there is a rabbit in here somewhere, so I couldn't go anywhere without a rabbit. So if you can tell me where the rabbit is, that would be absolutely lovely. I couldn't bring the real ones, unfortunately, and I didn't know how they'd be able to help, and it's raining. Nice to see you.
Goodbye for now.